Building alternative optimal portfolios. We have seen that the mean maximizing optimized portfolio may yield rather long tails, in other words, a rather risky portfolio. We could try to change the optimization profile in order to achieve a portfolio that minimizes the risk of losses, in other words, by minimizing the value at risk of the forecast portfolio. By achieving a portfolio that minimizes the length of the lower tail of the forecast value, we are achieving such an objective. And by minimizing the length, we actually mean to find the portfolio that shifts its left tail the most towards positive numbers. Since value at risk is usually defined at the 95% confidence interval, we can define the optimization objective as following: find the portfolio that maximizes the 5th percentile of the value of the portfolio at the end of the investment horizon. 116. Replace cells on the range C2:F2 with any values. Say 20 ounces per metal. 117. Write maximize mean on cell I2. We will not change this portfolio that has been already optimized with the automatic method. 118. Write maximize P5 on cell I3, the name of the next portfolio we will attempt to optimize. 119. Go to Risk Optimizer model definition and change the optimize field to percentile, X for given P. Write 5% on the respective pop-up field. 120. Close the Risk Optimizer window with OK. 121. Change iterations back to 300 in order to speed up the optimization process. 122. Proceed to start the optimization process. After some 9 minutes of optimization and stopping the process, the recommended portfolio looks as the following. 123. On cell I3 write maximize P5. 124. Write these values respectively on cells J3:M3. Gold, 105. Silver, 787. Platinum, 52. Palladium, 52. 125. On cell M3, insert the following function, equals risk percentile G284, J5, H3. This formula will calculate the 5th percentile of the output variable at G284, as referred from cell J5, evaluated on the second simulation on H3. Eventually, when we compare alternative simulations on a single run, we will see why this last parameter is necessary in this formula. Before stepping to compare this portfolio against the previous one, let's build a third portfolio. We could also think, from a more traditional perspective in finance, that by minimizing standard deviation, we might be creating a risk-minimizing portfolio. As we will see here in this example, this is not necessarily true. 126. Replace cells on the range C2:F2 with any values. Say 20 ounces per metal. 127. Write the name of the next portfolio we attempt to optimize, minimize standard deviation on cell I4. 128. Go to Risk Optimizer model definition and change the optimization goal to minimum. 129. Change the optimize field to standard deviation. 130. Go to Constraints and click on the Edit button, in order to change this constraint. The comparison operator should be inverted. The range to constrain, cell G260, should be larger than or equal to the constraining value, L5. This is because, if we were to leave this constraint as it was, the optimization process would eventually end up creating a minimum-sized portfolio of 10 units per metal. Standard deviation is an absolute, not a relative measure. Therefore, the software would attempt to minimize the positions of each asset in the portfolio all the way down to its lower limit, in order to achieve a minimum standard deviation. By changing this constraint in such a way, the optimization process will eventually modify the metal positions to a point in which the total value of the portfolio is slightly larger than $200,000. 131. Place iterations back on 300 and proceed to start an optimization after these changes have been accepted. At the end of the optimization, after some 20 minutes, Risk Optimizer generates the following portfolio. Gold, 111. Silver, 1997. Platinum, 49. Palladium, 14. 132. On cell N4, insert the following function, equals risk standard dev, G284, H4. This formula will calculate the standard deviation of the output variable at G284, evaluated on the third simulation, as referred to from H4. Soon, when we compare alternative simulations on a single run, we will see why this last parameter is necessary in this formula.